Hi, I'm Professor Angela Rasmussen from the Electrical and Computer Engineering Department at the University of Utah. In this example, I'm going to show how to design a system that uses op amps to describe this mathematical equation here. So as you notice that there are four inputs, V1, 2, and V3, V4, and it can use any combination of amplifier summers, subtracting amplifiers, switches, comparators, followers, etc. So first we want to see, is there an op-amp configuration that can actually implement this in one op-amp? So from what we know, when we have multiple inputs, there is a non-inverting summer, an inverting summer, which gives you all of negatives, summations, and then there's a difference amplifier, which does a subtraction function. So there's not one that's going to give us both, all four as inputs in. So we're going to have to kind of split this off. So this is not a unique answer, but one solution that I'm going to show here would be to possibly lump this up into a block that actually gives you out the 3V1 plus 2V2. This would be one option, and the inputs would be the inputs V1 and V2. We could then lump these together as a difference amplifier and actually kind of do these in parallel. So into this block would be V3 and V4 input, and out of it we would get the 5V3 minus 7V4. Then we would need to combine these outputs into another block that adds them together so that out we could get the summation of both of those, 3V1 plus 2V2 plus 5V3 minus 7V4. And that would be a solution. So this would be just summing these with no gain on either one, where this is one input and this is another input. And the gains on each of these would just be a coefficient of 1. So this block could be implemented by a non-inverting summer. This one would also be a non-inverting summer. And this would be a difference or subtracting amp. So let's look at those. Let's look at the op-amp difference amp since I have that one here first. So this would be the configuration of it. And I need both sides of the card to do the design. And from this we want the 5V3 minus 7V4. So we need to identify the different parts of this. So coming into this is our V3 and V4. So we would put V3 on this wire, and this is my V4. So coming into this wire would be V4, and coming in here would be V3. I then need a gain of 5. And so this is the equation that describes the output from this card. So it's G1, 1 plus G2, and then in our case the VTH1 is going to be our V3. So this would be what would be multiplied by V3 minus the G2 times, in our case, V4. So this one is V4. So I notice here that this G2 has to equal the same coefficient as that, so this would be a 7. If that's the case, this would be 7 here, and then this quantity would be 8. And the only way to get 5 out of this whole thing would be if G1 was 5 divided by 8. Because 5 divided by 8 multiplied by 8 would give me 5. So now I can look at the equations. So G1 here is RB over, let me erase that. So it's RB over RA plus RB. And again, RTH, there's not an input coming into this one. So we have that this 5/8 is equal to RB over RA plus RB. Therefore, we could choose RB as 5K and RA would be 3K, and that would achieve the 5/8. For G2, we look at that equation, and on this side of the card we see, again, there's not an RTH2, so we have RF over RS, and that's going to be this 7. And so if RS is 1K, RF could be 7K to give us that ratio of 7. So this would give us that difference amp to achieve the 5V3 minus 7V4. So I can just, in your case, you're going to just redraw this section. I'm just going to copy it here. This is my difference amp, and then I had V3 coming in from the left, V4 was coming in from the bottom. And I'll plug in these values here. So I had RB is 5K for this one, 3K. This is my V3 signal coming in, my V4 coming in, and RS was 1K, and this is 7K. So those are my values for this one. And now I can look at, this includes the difference subtractor. Now we need the non-inverting summer. So these are the cards for the non-inverting summer. I'm putting 2 of these because we need to design this twice for different conditions. So for the first one, we're going to have V1 and V2 coming in, and then we want 3V1 plus 2V2. Let me write that up here. 3V1 plus 2V2. And coming in, we have V1 on this layer, and then we're going to put this one as V2. So our overall equation is described by this. So we have G times G1 V1 plus G2 times V2. And we note that G1 and G2 have to be less than 1. So one way to achieve that is, sorry, that was G1. So one way to do this is to set G as the summation of both the coefficients, and then take the ratios for G1 to achieve 3 V1, so 3/5 times 5 would give me 3, and G2 would be 2 over 5 in order to get 2 V2. So we can look then at the equations themselves. For G2, that equation, again, we ignore the RTHs. G2 would be RA over RA plus RB. And an RA of 2K and an RB of 3K will give me 2 over 5. Of a ratio of that 2 over 5. For G1, the equation is located here. Again, we don't have the RTHs, and it's RB over RA plus RB. And we just check that the RB of 3K and RA of 2K would give me the 3/5, and it does. So these are going to be my values for RA and RB. For G, the equation is RS plus RF over RS. So if we use an RS as 1K and an RF of 4K, we'll get the ratio of 5K over 1K for that ratio of 5. And so that would be my design for this non-inverting summer. So I'm going to again just copy this section of the card and plug in those values. So I had V1 was coming into this signal, V2 into this one, and my value for RS here was 1K, RF is 4K, RA is 2K, and RB is 3K. So now I need the last op amp, which is going to be this non-inverting summer. But here I need coefficients of 1 for both of these just to sum together. So in order to get let me take this down. I'll do this design down here. So we want basically the inputs are going to come from both of those two sections. So coming into this one will be the 3V1 plus 2V2. And coming into this will be the difference one, which was 5V3 minus 7V4. And that will come into this side. So again, this equation, but now we want this to be coefficients of 1. So if we sum, again, the coefficients for G is going to be 1 plus 1, so I'm going to get 2. G1 will be 1/2 to get 1, and G2 will also be 1/2. So again, G2 equation, RA over RA plus RB, and this one will be RB over RA plus RB. So we can see if we have RA and RB are both 1K, that will give us the right ratios of 1/2. G is the RS plus RF over RS. And so if we also put RS equal to RF equals to 1K, we'll get that too. So for this one, I have coming in here, erase these, there we go. So this is going to feed in as this input here, this first input, and this will come in as the second input. And then all of these are 1K. So this resistor will be 1K, and all of these resistors are 1K. And then this is going to be my output VO. And so this will conclude my design for this circuit.